started to talk about permutation and symmetry groups in the last video, and the video was particularly focused on the idea of permutation groups, which talks about mapping a set to itself in such a way that we have a set mapped to different permutations of itself, and we discovered that the order of the permutation of a set is so all the possible permutations, right? The collection of all the possible permutations of a set, we discovered that would be the symmetry group, right? And we said that the order of the symmetry group is actually the number of elements of the set factorial. That is, if there are four elements in a set, the order of its symmetry group, which is a collection of all its possible permutations, would be would be 4 factorial, which is 24. So in that light, still talking about permutation and symmetry groups today. I mean, in this video rather, I'm talking about dihedral and symmetry groups. Dihedral and symmetry groups is what we focus on here. So first of all, we talk about symmetries of polygons. Don't forget that a polygon is a plane figure with three or more sides, and that is why a triangle is the smallest polygon you can ever think of. So when we talk about symmetries of polygons now, a symmetry of a geometric figure is a transformation that preserves the figure's shape and size. So imagine that we have a square, if we have a square like this, we are going to talk a lot more about square even beyond this particular point. So imagine this is a square. I mean, that's not a perfect square, by the way. That's not a square. So if I'm taking four sides here, should also go four here. Yeah. So now this is a square. Okay. So when we talk about the asymmetry, anything, uh, if you talk about the symmetry of this square, for instance, any if you cut the square in any way that makes sure you have the two sides equal, then you can say that's a so you can say those two parts are asymmetric. So for instance, if I draw a line like this, so you see this part and this part are basically the same thing. On the other hand, what if I draw a line like this? So this part is the same thing as this part. What if I come here and say and draw this diagonal line? Okay, this part is the same as this part, right? I could also come over here and draw another diagonal line like this, right? Such that this part and this part are the same. So these are lines that of symmetry, they make the square symmetry. They divide the square into two equal parts. So for a regular polygon, a symmetry is a distant preserving bijection of the plane that maps the polygon onto itself. So the set of all symmetries of a figure forms a group under composition. So like all the possible symmetries of a figure forms a group under composition. Just like all the possible permutations of a set actually form the symmetry group, then we say that the set of all symmetries of a figure forms a group under composition. So the next thing we'd like to talk about will be types of symmetries. Types of symmetries. So for a regular polygon, that is, a polygon is an n-sided shape, right? Where n is three upwards. So there are two fundamental types of symmetries there. First of all, we talk about rotations. So that is turning the polygon about its center. That is rotation. And then you have reflections, flipping the polygon across an axis of symmetry. Okay. So um for a square now, you can rotate this square. Okay, let's assume that you have A, B, C, D. If you call this A, B, C, D, okay, so you can rotate it about its axis, for instance, and then maybe you can rotate it such that, B takes over the place of A. So we now have like B, all right, we now have like B. Okay, I'll just use a smaller square to demonstrate. So just assume that this is the same square, but it's not the same scale, not never mind. So we can rotate, like we then have B, A, C, D. So that's that. You can rotate again. You can keep rotating, you can keep rotating like that, and then you can also rotate such that you then have this here. So this is now B. So A, okay, now this is it. Something is not right here. A, B, C, D. Okay, this is not even. nice in the first place. This is A, B, C, and D. Okay. So if you rotate it that way, so you have shifts like that. So that will now be A. Okay, A won't be here again. So A is now here. So you now have A, B, C, D. So you can also move it. What if you move it this way now? So B moves over here. So you have A, B, C, D. That's the idea of rotation. And then you can also have reflection, right? Reflection across the symmetry. So it's like you're flipping it over across the line of symmetry. So we're going to see things like that as we go on in this particular place. So basically, there are two types of symmetries for a polygon. You can either have rotations or reflections. Basically, that's the essence. So you can have rotations or reflection, where rotations talk about turning the polygon about its center. And then you can have reflections, which is flipping the polygon across an axis of symmetry. So you flip it over across the axis of symmetry. So, you have this, say you have this is a possible axis of symmetry now. So if you flip it uh, over that, you get a reflection. So let's talk about rotational symmetries now. For rotational symmetries, we can go like this. Let R denote the rotation by an angle. So if you rotate is a polygon by an angle 2 pi over n, that's talking about the possible number of sides the polygon might have. So let's rotate polygon by an angle 2 pi n, 2 pi over n. Let's imagine we are talking about a square, for instance, because we talk about regular polygon. So this is 360 over 4, which is 90. So if you rotate it 90 degrees, so then you can say R raised per k is rotation by, so R is rotation by an angle 2 pi over n. Then if you rotate it, R raised per k now is rotation by 2k pi over n. So you just multiply this by k, right? So there are exactly n rotational symmetries. So for every polygon, there are exactly n rotational symmetries. You have the identity, which is the original state. Then you have R, that is you rotating it, that is R raised per 1 rotation. Then you have R raised per 2 rotation, and that goes all the way down to R raised to the power n minus 1, like that. So where E is the identity rotation, that's the original position, like I said already. Okay, so if you have so this n now, at the end of the year, still going to have n possible symmetries, because now you move from the identity down to a step short of n itself. So but the identity still makes up the number to n, because from R to n minus 1 is n minus 1 plus this one, that's n minus 1 plus 1, which is still n. So E is the identity rotation, don't forget. So look at this example. So it's talk about the rotations of a square. Okay, a square has n equals 4 sides, as you know. So the rotations will be E based on what we have here now up there. So the rotations are the identity, then R raised to power 1, R raised to power 2, and R raised to power 3. Okay, so where R now is rotation by 90 degrees. R is rotation by 90 degrees. So the square has 4 rotational symmetries. So the square has 4 rotational symmetries. And the idea is that, you can rotate this, you can keep moving it, right? So you can rotate it the first time, and you have AB, you can rotate it the first time, right? And you have this move. So instead of ABCD like this, or we can even go clockwise, anyhow you want to go. So if you come back and you could do anti-clockwise, but let me do clockwise, for instance. So you can move it the first time, okay? You can rotate the first time, and then you have A, B, C, D. Then you can go second time. Say now, after that first rotation, you now have the second stage rotation. Now, what happens here is you now have, instead of A, B, C, D like this, you now have A, B, C, D. So after this, you can go again, another one. So you have so instead of having A start here, you have A, B, C, D. So we keep moving until we come back to the original position, and then we stop. So I guess you can rotate it one more, right? Can we rotate? Yeah, let's see. Can we rotate one more? So if you go now, the A starting from here. Okay, now we are back at the original position. So we have, so if you rotate one more time, right, you are back at the original position because now you have this A now moves here. You have A, B, C, D. So those are the possible rotations like that. So that's why this is all you have. But we will not worry about this because this is the first one, second, third, and fourth. So in essence, you can say, or better still, if you leave it like that, don't forget that this is E, the original. This is R when you rotate the first time. This is R. This is R raised to power 2, and this is R raised to power 3. And that is why but the possible rotational symmetries are E, R, R raised to power 2, and R raised to power 3. These are the possible rotational symmetries for a square, that is. All right. So that's how that works. So because each rotation is for 90 degrees. So we have four rotational symmetries like we saw there. So now we come to the idea of rotational symmetries. So how do we deal with rotational symmetries? A reflection, reflectional symmetries. A reflection flips the polygon across a line, that is across the axis, through its center, right? So a regular polygon, of course, a polygon is like n gone has exactly n reflection symmetries, and let's denote one such reflection. Let S rather denote one such reflection. So R denotes rotation, S denotes reflection. Okay. So when we talk about reflection, rotation is you moving over. So when you talk about reflection, it's like um, now for me that that would be a bit. Uh, I'm trying to see how I can do this. So I'll just try to, as much as possible to give an example. For instance, if you want to do a reflection of this now, if you want to do a reflection of this, it might be something like this. So for a reflection now, so one such reflection is, so because you're flipping it about any of the symmetries, like if you flip it about this particular symmetry, um, you might get something like about the symmetry. I'm trying to see. So, you have B here, but instead of the B being like this, it's going to be the opposite. It's going to be like this, that's B because it's reflection. And then A now will be here. So I think A remains there no matter how you look at it. And then C comes like this, and instead of the regular D, you have something like this. That's the idea of reflection. So it's like when you see yourself in a camera, something like that. And that there are four such possibilities. That's what we are saying. In fact, I want to believe that you have each possibility will coincide with each rotation you have. So this one is for the original. So if you want to have this now, you know okay, well, I think I can even work that out. Okay, yeah, this is with this, like, I think it's helpful. So if I still have this now, another possible rotation is, so it's like there's a reflection that corresponds with each rotation. So this is for the original one, but for the next one now, you have this now. So this A, because if you flip it, okay, okay, maybe it's more like you now have A here, and then you have D here, but the D is like this, and then this is C, and this is B, and so on and so forth, right? So those are the kind of things reflection would talk about. So let us denote one such reflection, right? So imagine this now, reflections of a triangle. So for a triangle, a regular triangle has three reflection axes. Thus, it has three reflections, S, RS, and R squared S. And each reflection reverses orientation. So each reflection reverses the orientation. So of course, we already know for an equilateral triangle, you have this idea. You have this now. This may not be perfectly equilateral, but just get the idea. This is ABC. Of course, we already know for rotation. For rotation, it just means you have, maybe you now have A, sorry, you now have A, B, C. Another one, you have A, B, C. That's for rotation. But for reflection, so that I think there are three possible symmetries there. This one going, this one, and this one. Okay, so things like that, and then flipping this about the axis now. So I maybe ending up having something like this now. So for this first one, I maybe now have like B, and this is A, and this is like C. So that's the idea of reflection, and so on and so forth. So, and we have three possible reflections in that case. So each reflection reverses orientation, like we said there. So let's talk about the general idea of dihedral groups, because the topic is about dihedral and symmetry groups. So dihedral groups Dn now. So the dihedral group Dn is the group of all symmetries of a regular polygon. So that means you're putting together all the rotational and reflectional symmetries together. So if you put all the rotational and reflectional symmetries together, so in that case you have n rotations and you have n reflections, such that the order of the dihedral group Dn will be 2 times the number of sides the polygon has. And that means that all the possible, just like for we saw for a square, right? There are eight possible dihedral group. So for the dihedral group, D4 is the group of all symmetries of a square, and it will have 4 rotations and 4 reflections, like we already saw, and still going to talk about that. So, and then apart from that, we also have the elements of the dihedral group. So what are the elements of dihedral groups, Dn? So using generators, we have generators R for rotation and S for reflection. The elements are Dn, which is started from E. Now you have, of course, we already know for rotations we have from E to Rn, and for reflection, just like what we saw here, we have S, Rs squared. And that pattern goes on like that, depending on what exactly you have. So you just have S starting out, and then you have R. So if it was for R4, for instance, if you have 4 reflections, so that mean you have S, Rs, R squared S, and up to R cube S for a square. You're going to see that also as we forge ahead. So here now you have the N rotations and then the N reflections like this. So let's talk about fundamental relations in dihedral groups. So the group D sub n satisfies the relations that Rn is equal to E. That is, if you rotate 4 times a square, if you rotate a polygon, the number based on the number of sides, it comes back to the original. And we saw that example when I tried this initially, right? So this is the original thing. So it rotates first time, second time, third time, and fourth time. That's n times. It comes back to the original, which we started with, that the identity, that it comes back to that. So that makes a lot of sense. So R raised power n is E. Then apart from that, S squared is E. So the second reflection is also E. And then, so this is always that the square of the first rotation is equal to the identity. Then SRS, that is the rotate reflection multiplied by rotation multiplied by reflection, gives you the inverse of a rotation, right? So this completely describes the structure of the dihedral group. So these are the identities, the functional relations rather, in a dihedral group, that the rotation raised to power the number of sides is identity, takes it back to the original. Then the square of the reflection takes it back to the original, and reflection multiplied by rotation multiplied by reflection. So it means if you reflect the first time, rotate secondly, and then reflect finally, you have the inverse of the rotation. So those are the fundamental relations. So let's look at example 3 now. So dihedral group D4, and that means a square now. So for a dihedral group C4, D4, which is for a square, D4 is identity element R1, R2, R3. That's talking about the 4 rotations. And then for the 4 reflections, you have the first reflection, rotation by reflection, rotation by the reflection, rotation squared by reflection, and rotation cubed by reflection, like that. So this S now, I mean, just like I said the other time, right? It's like this reflection is based on the original thing, then RS is based on the first rotation, and so on and so forth. So where R now is rotation by 90 degrees and S is a reflection. So the group has 2 times 4, which is equal to 8 elements. I mean, as expected. So let's see a practical example of this now. Gracefully, I got this from Wikipedia. So let's look at this. Since we're talking about a square, see, these are all the possibilities you can have for a square: the 8 reflections and the eight rotations. So first of all, this is the square's initial position, R naught. That is our what we call E, right? That is our E. This is the original thing. So imagine we have all these things, and a particular F is written here. So this will show us how the movement is happening. So you can have a rotation. First of all, if you do anti-clockwise rotation, you can have a rotation by 90 degrees. That means you shift this F, now shift it by 90 degrees all the way here. So you have this 90 degrees rotation, and then you can shift the 180 degrees from the original position, shift it all the way clear. You have 180 degrees rotation. So that F is pointing down this way. Then you can shift it next at 90 degrees. That's 270 degrees. That's all the way. So this is in that system now. This is what we called this will be E. This is R. This is R squared. This is R raised to power 3. So 90, in fact, this will be E. This is R raised to power 1. That's rotation by 90 degrees. R raised to power 2 is rotation by 180 degrees. And R raised to power 3 is 270 degrees. Now, with that taken care of, what about the reflections? So see the original position, right? So this original position now, if you reflect, you can reflect it about this line of symmetry. So horizontal reflection. So if you reflect this horizontally, this one it will flip over here, but then the F will be facing the opposite side. That's the kind of thing I was talking about before. Like instead of having this F like this, it now faces it faces the other direction. So instead of facing right, it faces left now. So that is horizontal reflection. Then we can have vertical reflection. So for vertical reflection, you then have so you see the original F now, you reflect it vertically. So instead of the base facing down, it's now facing up because you have reflected it vertically. And then you can also have diagonal northwest southwest reflection. So you reflect this same thing now, reflect it across this symmetrical axis. So and then the F is showing this way, and then you can also do northeast southwest reflection, and then you have this way. So those are the four. So you have the four rotations and the four reflections like that. So now next thing is to talk about presentation of groups. How do you present groups? So a group presentation describes a group in terms of generators and relations. So it is written as generators given their relations. So imagine presentations of a square now. So the presentation of Dn, the dihedral group has the presentation as follows. First of all, you have Dn, which is, so we already know this presentation, but this is just another way of talking about this. So you are presenting a dihedral group in terms of its relations, talking about the rotations and the reflections. So first of all, we know that Rn is E, is taken care of. I squared is also E. That's established. And then we know that SRS is R raised to power minus 1. So those are the presentations of Dn. So this means that every element can be written using R and S. That's all we are saying. So every element can be written using R and S. Then all relations follow from the three defining relations, right? So R raised to power n is E, S squared is E, SRS is R minus 1, R raised to power minus 1, like that. So we have an example here. I want to talk about the presentation of D raised power 3. I mean D3. That's talking about an equilateral triangle. So you have D3 talking rotation and reflections is such that uh, R raised power 3 is E. That is rotate it 3 times, you get back to the original position. Then reflect it twice, you get back to the original position. And then you have SRS is the inverse. R is the inverse of the rotation. So this group is isomorphic to the symmetric group on 3 elements. Okay. I mean the whole idea of isomorphism and all that, we'll talk about them in the future, in previous future videos. Now we talk about the idea of Cayley tables. A Cayley table displays the group operation for all pairs of elements. So all the possible pairs of elements you can ever have. So a Cayley table displays that. So you can have rows corresponding to left factors while columns correspond to right factors. So imagine a Cayley table for D3. That's a Cayley table for an equilateral triangle like that. So, of course, for an equilateral triangle, for a triangle generally, you're going to have three rotations and, of course, three reflections. Three rotations, that's the identity, the first rotation, the second rotation, and then the first reflection, second reflection, and third reflection, making six altogether because you know that's going to be 2 times 3, which is 6, and that's why we have this 6 here. So, we can then have the Cayley table for this D3 now. And seeing, so this set of elements, we have it horizontally, and then we have it vertically here, and we have it horizontally here. Identity by identity will be identity. Identity times anything remains that. So E identity times R is R. r squared, s, s. So identity times anything remains the same. Then when we come to r times identity will be r is r squared, r times r squared is r3, and we know r3 in d3 is actually identity again, right? Because that's the fundamental thing, that r raised power n is equal to e. Then r times s, of course, is rs. R times rs is r squared s. Then r times r squared s, that'll be r3s. And r3 is identity times s, which identity times s will give us s. Then here we have r2. R2 times a remains the same. R2 times 3 is r3, which is e in d3. Then r2 times r squared, of course, to just keep increasing the power. Just increase the power of r as you move on. So r squared times r squared, you have r4. And r4 is r3 times r. R3 is e times r, which is r finally. Then r2 times s, r2s, r2 times rs. So that's r3s. R3 is e, then with the reflection s. And then you have r2, r3. I mean r2 times r2s, that's r4s. So that means r3 times r times s. So r3 is e. E times rs remains rs. And then you go on like that. S times e. So you just follow the rules. So, but for here, now pay attention that, yeah, okay, well, let me just keep going. S e is a e is s. S times r is r squared s. S times r squared is s times r. This should actually be rs, right? S times c is s, yes. S times r is should be rs. I think this should be rs. Let's see to that. So s times e is s, of course. S times r is should be rs, yes. Then s times r squared should be r squared s, r raised to power 2s. Then s times s, I think this should be fine now. So I think this should work now. Yeah. So S again, SE is S, SR is RS, SR squared, that's R squared X. Yeah, now that makes sense now. S times S, we already know that generally S squared is E also, like we already know. So S squared is always E. So the second reflection is E. So if you reflect something twice, it comes back to the original position. That's what we are saying. So S is E, then S times RS. That's S times rs should be r because s squared is e. So this should be s times rs is rs squared. So this should just be s times rs should be rs squared. So this should just be r, whereas this should be s times r squared. So this should be r squared now. Okay. Yeah, based on the rules, that is what we should have. So I go again. SS is S, SE is S, SR is RS, SR squared is R squared S, SS is E. That's, yeah, S squared is always a yes. S times RS, that is RS squared. And S squared is E, so we have only R left. Then SR squared S, that's R squared S squared. So S squared is E, so we have R squared left. Then here too, we have RS is E, RS times r, that's r squared s. Okay, what's happening? Rs, yeah, then it should be r squared s, r squared s, yeah. And coming here, rs times rs should be r squared s squared, and s squared is 1, so this should just be r squared, I believe. Rs times, okay, I think this should be fine now. Okay, we'll keep correcting as necessary. So as far as we understand the rules, that makes sense. So rs times e is rs. Rs times r is r squared s, yes. Rs times r squared is r cube. Rs times r squared is r cube s. R cube is e, so this will just be s, I believe. Rs times rs times r squared, that's r cube e. So r, that's r cube s rather, and r cube is e, so this is just going to be s, then rs times s, that is rs squared, which is just r. Rs times rs, that's r squared s squared, so this will just be r squared, to be r squared. Then rs times r squared s, that is r cube s cube, so everything will just be e. Okay, then let me do this. So this is r squared s times e, yes. then r squared s r, that is r cube s. So this will just be s. Then r squared s r squared, that is r, that should be rs, all right? Because r cube is e, then times r, right? So r raised by 4 is r cubed times r. So r cube is e. So we have r left and then s. Then coming here, we have r squared s squared. R squared s squared is just r squared. Yes. And then coming here, we have r cubed, which is e, right? And then s squared, which is also e. So we have just e left here. Then coming here, we have r squared, r squared. That is just r in that case. Then s, that is e. I think this is how they should be. Okay, I'll go over the last two rows again to be sure everything is fine. So we have that RSE is RS, then RSR is R cube S, yes, and R cube is E. So we have just S left. RSS, that is RS squared. S squared is E, so we have only R. Then RSRS, that's R squared S squared. That's R squared because S squared is E. Then R squared S. So that's R cube S squared. So R cube is E, S squared is E, so everything is E. Then coming here, we have R squared S E. Of course, that's the same thing. Then R squared S R, that's R cube. R cube S, that's why we have only S left here. Then R cube R squared, that's R cube R cube is Z, so we have RS left, correct? Then R squared S is R squared S squared. All right, that'll be R squared E because S squared is E. Then R squared S RS. So that's R cube S squared. Everything is E there. Then that's the identity. R squared RS, R squared S, R squared, that's R4 S squared. Of course, S squared is already E, gone. Then R4 is R cube R cube is E. So we have E multiplied by R. And that is R left. Okay, that's the Cayley table for an equilateral triangle D3. So, observation from Cayley tables. Now, you discover that the dihedral group Dn is non-abelian for n greater than or equal to 3. So, for n greater than or equal to 3, the dihedral group is non-abelian. So, it means that if you multiply forward, it's not abelian in short. So that means the idea of abelian is if you do A, B, it's not the same thing as BA, basically. Then rotation elements form a cyclic group. I know a cyclic group is formed by just it's generated by a single element. So rotational elements form a cyclic group. Then reflections do not commute with rotations. Okay? Reflections do not commute with rotations. So if you do rotation first and then reflection later, you don't get when you do reflection first and rotation later. So in summary, we see that symmetries of regular polygons form groups. All right, symmetries of regular polygons form groups, first of all. Then dihedral groups, they capture all rotations and reflections. The order of the dihedral group Dn is actually 2 times the number of sides of the polygon. Then group presentations give compact algebraic descriptions, and Cayley tables visualize group structure concretely. So on that note, we have these 10 practice questions as usual. You want to try your hands on them to be sure you really get the idea we've talked about in this video so far. Okay, so first of all, list all the elements of D5 in the form RK and RK4. Of course, you know that'll be E, R is power 1, R is power 2, R is power 3, R is power 4. That's 5 rotations. And then you have the reflections. You have S, then you have RS, you have R squared S, R cube S, and R4S. Those are the, uh, I mean, did I say the first one are the rotations are E, R is power 2, R is power 3, R is power 4. Those are the rotations. The reflections are S, RS, R squared S, R cube S, R is power 4S. Those are the reflections. Putting everything together, you have all the elements of the dihedral group D5. So for D6, what is the order of R2? You want to check all of that out. Okay, so in D4, compute SR3 in the form RKS. Then if in Dn, show that SRK is R is power minus KS for all integers K, and so on and so forth. So you want to try your hands on this to be sure what happens there. So in D5, what is R2S squared? Of course, R2S squared is going to be R4 S squared. So R4, you need R5 to be E in D5. So this is R4. So you're going to just have, but S squared is always E. So R4 S squared will simply be R4 because S squared is going to be E automatically. So imagine here in D3, compute R squared S and simplify to one of this. Of course, this is R cubed S squared. So R cubed in D3 is E because that's N is 3. So R cubed is E, S squared is also E. So at the end of the day, R squared S is simply E, just like we have been used to. And so on and so forth. So try your hands on it. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I thank you very much for that. If you have not, what are you waiting for? Go ahead, subscribe right now and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you some special privileges. Ultimately, don't forget to comment, like, and share so that other people can have access to the great content I have going on here. Till I come your way again, keep doing math right. Bye.